Today we are going to be introducing the basics of field effect transistors, or FETs for short, specifically focusing on metal oxide semiconductor field effect transistors, or MOSFETs. Field effect transistors are transistors that use an electric field to control the current flowing through the transistor. They are voltage-controlled devices, as opposed to bipolar junction transistors, which are controlled by current and voltage. There are two main types of field effect transistors: junction FETs, or JFETs, and metal oxide semiconductor FETs, or MOSFETs. JFETs were the first type of FET created, but have now been largely superseded by MOSFETs. MOSFETs are by far the most widely used transistor today. They are easy and cheap to manufacture and can be made extremely small. In 2012, MOSFETs with a key dimension only 22 nanometers wide were released. This translates to fitting approximately 4,000 of these devices within the width of a human hair. New generations continue to come every approximately 2 years that have even smaller dimensions, allowing even more transistors to fit within a given area. MOSFETs, like most transistors, are generally three-terminal devices. The three terminals are the gate, G, drain, D, and source, S. MOSFETs sometimes include a fourth terminal, which can have secondary effects on performance. The optional fourth terminal is known as the body, B. In general, we will assume that the body terminal is connected to the source, and so generally ignore the body connection. Transistors, in general, are devices where one terminal controls the current flowing through the other two terminals. In MOSFETs, the gate is the controlling terminal. The gate was originally made out of metal, hence the metal in the metal oxide semiconductor name. An insulator, the oxide, again hence the second word in the name metal oxide semiconductor, is placed between the gate and the channel where current flows. The insulator largely prevents current from flowing into or out of the gate, hence why these are voltage-controlled devices. The fact that almost no current flows through the gate results in MOSFETs with very large input impedances. These tend to be on the order of 10 to the 12 to 10 to the 14 ohms, i.e. in the range of teraohms. There are four major types of MOSFETs that break down based on their primary charge carrier and whether they do or do not conduct current by default. In the first dimension, there are N-channel devices, often abbreviated NMOS devices, where electrons, i.e. negative charges, are primarily responsible for the flow of current, and P-channel devices, abbreviated PMOS, where holes, i.e. positive charges, are primarily responsible for the flow of current. In the second dimension, transistors can be either enhancement or depletion type devices. Enhancement type devices are off by default, i.e. current does not flow with a default gate connection. Applying a voltage to the gate enhances the ability to carry current, turning the device on. Depletion type devices are on by default. Applying a voltage at the gate can deplete the current carrying ability and turn the device off. We will be focusing primarily on NMOS enhancement type MOSFETs, but it is good to be aware of the different possibilities. All four transistor types have a number of similar but slightly different symbols used to indicate the transistor. In this first set, the arrow points from the P-type material to the N-type material in the device and can be used to determine P from N-type devices. In the second set, which we will primarily use, the arrow points in the typical direction of current flow under normal usage. Finally, in this last set, there is no arrow. Instead, the transistor type is indicated by the absence or presence of a circle at the gate. This set of symbols is typically used in the context of digital logic gates. The circle, or 0, at the gate of the PMOS device indicates that the device turns on when a low voltage, or logic 0, is applied to the gate. The figure here shows the general cross-sectional construction of an N-type enhancement MOSFET. The transistor is composed primarily of a large block, i.e. the body, of P-type silicon. Into the body, two regions of heavily doped N-type silicon are created to form the source and the drain. To form the gate, an oxide layer, typically silicon dioxide, is placed over the channel region between the source and the drain. A gate conductor is placed on top of the oxide. By applying a potential difference between the gate and the body, the conductive characteristics of the channel region between the source and drain can be changed to allow current to flow. For a moment, we will focus just on the channel region between the source and the drain and how the region changes as a voltage is applied between gate and base. If a small positive voltage is applied between gate and base, the positive potential at the gate repels positive charges, creating a region with a small negative charge known as the depletion region. As VGB is increased, the depletion region grows. When VGB is increased beyond some threshold voltage, a dense inversion layer of electrons forms near the gate. This provides a conductive channel between drain and source, which allows current to flow between the source and drain as a voltage is applied across the two terminals. We will now look at how a MOSFET behaves as different voltages are applied across the terminals. As mentioned previously, the body, B, is generally internally connected to the source. This means that the gate base voltage, VGB, is the same as the gate source voltage, VGS. To create the inversion layer previously mentioned, VGS needs to be above the threshold voltage. If VGS is less than VT, then no inversion layer is present, and so no current can flow between source and drain, and the transistor is said to be cut off. Looking broadly at the whole transistor, similar to diodes, a depletion region forms between the N and P-type silicon in the transistor. When VGS is greater or equal to the threshold voltage VT, the inversion layer previously mentioned forms between source and drain. If the drain voltage VD is greater than 0, the positive charge at the drain pulls electrons away from the channel to be more sparsely distributed around the drain. This is why the inversion layer near the drain is smaller than near the source, and why the depletion region near the drain is larger than by the source. In this region, where VGS is greater than VT and the drain source voltage VDS is small, i.e. less than VGS minus VT, the transistor is in the triode region, also sometimes called the ohmic or linear region. These two latter names somewhat correspond to the fact that in this region the transistor behaves as a voltage-controlled resistor, where the voltage VGS controls the resistance of the resistor. As VD is increased, the depletion region near the drain continues to get larger, and the inversion layer near the drain continues to shrink. At some point, the inversion layer near the drain entirely disappears. The drain at this point is said to be pinched off. While there is no inversion layer near the drain, current still flows between source and drain. The potential difference is so large between the terminals that electrons are able to push through the pinched off area that contains few carriers. Further increases in VD, however, result in minimal further increases in current as the additional potential is used to overcome the increased pinched off region. The transistor is said to be in the saturation region. Note that saturation region for a MOSFET is somewhat similar to active mode for a BJT, and that the triode region for a MOSFET is somewhat similar to the saturation mode of a BJT. Similar to BJTs, we can look at characteristic curves for a MOSFET to see how current through the transistor relates to different voltages. This first graph shows the drain current relative to the gate source voltage, VGS. When VGS is less than VT, the transistor is off, and so no current flows through it. When VGS is increased beyond VT, under a fixed VDS, the transistor will first enter saturation mode. At this point, VGS is still small, and so VGS minus VT is small and therefore less than VDS. As VGS is increased, VGS minus VT eventually exceeds VDS, and the transistor switches into the triode region. We can also look at the drain current versus the drain source voltage, VDS, for different fixed gate source voltages. This looks somewhat similar to a BJT collector-emitter junction characteristic curve. For a fixed gate source voltage, as the drain source voltage is increased from 0, the transistor first starts in the triode region, as VDS is relatively small, so VGS minus VT will be larger than VDS. The current ID continues to increase as VDS is increased until the drain source voltage equals VGS minus VT, at which point the transistor enters the saturation region and current increases much more slowly with any further increases in the drain source voltage. So far we've concentrated on enhancement mode and type MOSFETs. Other MOSFET types have generally the same behavior with some slight modifications. A P-type enhancement MOSFET has the same ID versus VDS curve, except that all voltage and current values are negative. To turn a P-type MOSFET on, the gate source voltage must be less than VT, and current will be going the opposite way from source to drain. In a depletion type MOSFET, current can flow between drain and source when the gate source voltage is 0. Hence why, with VGS equal to 0 in the graph, the current is positive for any positive VDS. By decreasing the gate source voltage, the transistor can be turned off. You should now have a general understanding of the physics behind metal oxide semiconductor field effect transistors and the different regions that MOSFETs can operate in.